So, dear students, we have studied about a few things into the last period. Let us revise that. We have started studying into the last period about the ionic radii. We know that as we go down the group, the ionic radii increases, but going from aluminum to gallium, the ionic radii decreases. We have even studied that the ionization enthalpy value also going from aluminum to gallium, it increases, and even in case of going from indium to thallium also the value of ionization enthalpy increases. We know that the third ionization enthalpy is greater than second ionization enthalpy, and second ionization enthalpy is greater than first ionization enthalpy. In case of boron, this sum of the first, second and third ionization enthalpy is very high, but in case of aluminum, this total of or the sum of the three ionization enthalpy decreases in case of aluminum, and that is why boron forms the covalent compounds, but aluminum can form the ionic compounds. Then we have studied about the electronegativity, my dear students. Going from boron to aluminum, the electronegativity decreases to a very great extent, that is 0.5, but the electronegativity value of gallium, indium, and thallium is almost similar. But still, we can say that going from indium to thallium, there is a marginal increase into the electronegativity. We have studied about the physical properties, like boron is the hardest one, and going down the group, the hardness, my dear students, the hardness decreases, the density increases. Gallium is a special element with the very low melting point, and that is why gallium can be utilized to into the thermometer to measure the temperature, where mercury fails to measure such a high temperature, because at such high temperatures mercury is available into the vapor form. Density of this element increases as we go down the group. Then we have started studying about the chemical properties. First, we have studied about the oxidation state and trend in chemical property or chemical reactivity, my dear students. As we have studied into this, that they generally show the group oxidation state +3, but in case of aluminium, the sum of the first three ionization enthalpy is decreased as compared to boron, and that is why boron make the covalent bond, but aluminum can make ionic compounds. And as we go down the group, the gallium, indium, and thallium, they behave like typical metal, and they form the ionic compounds. But my dear students, if we compare this polarization power, then +3 compounds are more covalent than +1 compounds. So +1 compounds are comparatively ionic, whereas +3 compounds are comparatively more covalent, because in +3 oxidation state, the ion has got more polarizing power, and that is why it polarizes the negative ions, and thus as it polarizes the negative ion, it forms more, or it creates more covalent character to the compound. As we go down the group, the stability of +1 oxidation state increases, and the stability of +3 oxidation state decreases. +1 oxidation state is most stable in thallium, but aluminum does not show +1 oxidation state at all. The stability of +1 oxidation state in indium is more than the stability of +1 oxidation state in gallium. So this is how, my dear students, we understand the stability of +1 oxidation state is maximum in case of thallium due to the inert pair effect. We have even seen, my dear student, that the +3 oxidation state in tin and other element is highly oxidizing. So in nature, +1 oxidation state is more stable in thallium, and that is why thallium +3 is highly oxidizing in nature, because it itself converts itself into Tl+1, so it itself is get reduced, and that is why it oxidizes the other substances. So we have even studied that these compounds, when they make the covalent bonds, their halides or the other compounds in trivalent situation, they have only 6 electron, and that is why they are electron deficient, and that is why they accept the 3 electron, or they accept electron pair from the outside. Thus they behave like Lewis acids, and this Lewis acid character, as we go down the group, my dear students, it decreases. You can see here that this BCl3, which was planar and for having sp2 hybridization, when it accepts the lone pair from the ammonia, it forms the sp3 hybridization and it turns out to be tetrahedral in nature. The bond between nitrogen and boron is a coordinate covalent bond. For this bond, all the electrons are given or all the electrons are donated by nitrogen. AlCl3 achieves its stability by making a dimer. So this AlCl3, two AlCl3 combine with each other to form Al2Cl6, which is a dimer. You can see here by looking into the bond parameters, the bond length with this bridge bond is longer. So this is what it is known as the bridge bond, and this dimer is known as the bridge dimer. Bridge dimer. We have even seen that in trivalent state, most of the compounds which are covalent in nature, they undergo the hydrolysis. So when they undergo hydrolysis, they form MOH4 minus kind of complexes. For example, BCl3 undergo hydrolysis to produce BOH4 minus 1 complexes. Aluminum can make AlOH4 minus 1 complexes. But apart from this, my dear students, aluminum even can make, when undergo hydrolysis process, aluminum undergo aluminum is hydrated also, and when it undergoes the hydration, it forms sp3d2 AlH2O6 plus 3. By vacating its OR orbital, the 6 water molecule donates their electrons and make this octahedral AlH2O6 plus 3 complex. We have even studied by using by solving one of the problem that when we if we look into the electrode potential of aluminum plus 3 oblique aluminum is negative minus 1.66, and the electrode potential of thallium plus 3 oblique thallium is plus 1.26. It shows that plus 3 oxidation state is more stable in aluminum as compared to the thallium. But not only plus 3 oxidation state in thallium is unstable, but it is highly oxidizing in nature, and it can be easily converted. Thallium plus 3 can be easily converted to Tl plus 1, and that is why it is a very good oxidizing in nature. So this is how, my dear students, we have studied about the oxidizing nature of our Tl plus 3, and now we want to start studying about the reactivity towards air. So let us study the reactivity towards air. Boron is unreactive in the crystalline form. Please remember that due to the very high ionization enthalpy, and this boron is unreactive into the crystalline form. Aluminium forms uh, boron is unreactive in the crystalline form. Aluminium forms a very thin oxide layer on the surface which protects the metal underneath to go from the further attack, and that is how aluminium become unreactive by making a protective layer of oxide Al2O3. Amorphous boron and aluminium metal on heating in air forms B2O3 kind of oxides. So boron will make B2O3 and aluminium will make Al2O3 respectively. They also react with dinitrogen at high temperature. So these metals or these elements from group 13, they react with the dinitrogen to form the nitrides. But remember that these elements form dinitrogen only at elevated temperature or at very high temperatures. So element of group 13, they react with nitrogen to form the dinitrogen. So when they react with dinitrogen, they form dinitrides, and for this we can write this general reaction, my dear students. For the formation of oxygen, we can write 2E plus 3O2, that gives 2E2O3 solid, and for nitrogen we can write 2E plus N2, that gives 2En. So my dear students, you can see that aluminium generally forms ALN kind of nitride. Aluminium generally forms the ALN kind of nitrides, and all these elements form these nitrides into the plus 3 oxidation state. So this is how, my dear students, we understand the formation of nitrides by these elements of group 13. The nature of these oxides varies down the group. Now we need to understand the nature of the various oxides formed by these elements. So let us study about the nature of these oxides. How do they differ with each other? Boron trioxide. Boron trioxide is acidic in nature. That means boron is a non-metal and reacts with basic metallic oxides forming metal borates. So boron trioxide is acidic in nature. Aluminium and gallium oxides are amphoteric, and those of indium and thallium are basic in nature. So aluminum and gallium, they slightly show the non-metallic character also, because their oxides can react with both acid as well as base, so their oxides are amphoteric in nature. Whereas the oxides of indium and thallium, they are completely basic, so we can say they behave like a typical metals. Now we want to study about the reactivity towards acid and alkalis. Boron does not react with acid and alkalis even at moderate temperatures. So boron behaves non-reactive towards acids and alkalis due to oxide layer formed on boron. So boron forms an oxide layer, and that is why it does not react with the acids and alkali. Aluminium dissolves in dilute hydrochloric acids and liberate dihydrogen. My dear students, this is the uh, reaction which is very important and quite a few times asked into your various exams. So these two aluminum reacts with 6HCl to form 2Al plus 3 and 6Cl minus. These two combine to gives us AlCl3, 2AlCl3, and three molecules of hydrogen gas are also being produced. So this reaction was the reaction of aluminium metal with the hydrochloric acid. We are very well aware that metals, when react with acid, they produce hydrogen gas. Thus aluminum behaves here as a metal, and it produces hydrogen gas when it reacts with hydrochloric acid. However, concentrated nitric acid renders aluminum passive. We have studied in 10th standard also the process. When aluminum reacts with nitric acid, it makes the layer of aluminum oxide. We have studied this process under the name of the anodizing process. So due to the anodizing, my dear students, or when this aluminum is dissolved into the nitric acid being very good oxidizing in nature, it makes, or uh, aluminum makes a protective layer of oxide on the aluminum on the surface of the aluminum. Aluminum also reacts with aqueous alkali and liberates dihydrogen. This is a very important reactions for aluminum, my dear students, that when this aluminum reacts with the alkali like sodium hydroxides, you can see that 2 aluminum reacts with 2 NaOH and 6 H2O to gives 2 NaAlOH 4 minus. This compound is known, or the name of this compound is sodium tetrahydroxo aluminate 2, and it also produces hydrogen gas with the alkali. So aluminum behaves as a metal and produces hydrogen gas when it reacts
सर
with
सर
alkali as well
सर
as
सर हमें स्क्रीन
alkali as well as acid. Now if you have any question you can ask me. Yes.
सर हमें
सर
स्क्रीन दिखने में
स्क्रीन
प्रॉब्लम हो रही है सर
सॉरी बेटा.
सर स्क्रीन स्क्रीन दिखने में प्रॉब्लम हो रही है सर
अच्छा, मतलब दिख तो रही है कि दिख भी नहीं रही
सर
है?
नहीं, स्क्रीन ही नहीं दिख रही है।
सर
सर
स्क्रीन
पहले
दिख रही है, जो आप स्टार्टिंग में दिखा रहे थे वही दिख रही
अब
थी।
दिख रही है,
ओके,
अभी
अभी
दिख रही
दिख
है,
रही
अब
है
दिख
कि
रही
अभी
है
भी नहीं
सर,
दिख रही है?
यस सर
अभी
अभी
दिख
ठीक
रही
है
है।
अब दिख रही है। सर स्टेबल है, कुछ हो ही नहीं रहा उसके अंदर, जो आप लिख रहे हो
बेटा
डिफरेंस दिख
कहाँ
ही
से
नहीं
ऐसा
रहा है
हुआ?
स्टार्टिंग से।
अरे यार, तो अब आप बता रहे हो।
अरे सर हमको लगा आप वैसा ही हो रहा होगा, इतनी देर से नहीं होता, अभी पता चला तो फिर अभी बोला।
ओके, तो ये समझ में आया है क्या? फिर से समझाऊं? Okay, let me show you very fastly that this aluminium, my dear students, reacts with acid as well as alkali. When aluminum reacts with 6HCl, it produces AlCl3, two molecules of AlCl3, that is 2Al plus 3 and 6Cl minus, and produces hydrogen gas. Same way, my dear students, you can see here that whenever however, concentrated nitric acid renders aluminum passive by producing the protective oxide layer. That is what we have studied into the 10th standard in the form of the anodizing process. Aluminum reacts with alkali, my dear students. So aluminum reacts with alkali and liberates hydrogen gas. You can see these reactions that when aluminum reacts with 2 NaOH and 6 H2O, it produces 2 NaAlOH for minus and 3 hydrogen. This compound is known as the sodium tetrahydroxoaluminate 3. Now, my dear students, we want to study the reactivity towards halogen. Now, can you see the screen, my dear students? I'm moving it.
Yes, sir.
Okay, that's great. So now we'll study the reactivity towards halogen. These elements react with halogen to form trihalides except TlI3. Dear students, thallium iodide is not possible at all. So please remember, thallium in +3 state does not form iodide at all. All the other halides are possible in case of thallium, as well as all the other elements like boron, aluminum, gallium, and indium. So only TlI3, thallium iodide, is not possible. Otherwise, all the other elements form, when they react with halogen, they form the halides of 2EX3 types. Now, my dear students, we have a question here to solve so that we can understand something better. White fumes appear around the bottle of anhydrous aluminum chloride, that is AlCl3. Give reason. So whenever we feel aluminum chloride in a bottle, we will see white fumes around it. What is the reason? Anhydrous aluminum chloride, that is, anhydrous means not having any water of crystallization into it. That kind of AlCl3 is known as the anhydrous AlCl3. So whenever we have anhydrous AlCl3, please understand, this is anhydrous AlCl3, or if we have AlCl3 into XH2O, that is what it is called, hydrated AlCl3. So this anhydrated AlCl3 is partially hydrolyzed with atmospheric moisture to liberate HCl gas. So it reacts with water and produces HCl gas and AlOH thrice, let's say. So, my dear students, when it reacts with the water present in the moisture, it liberates HCl gas, and this moist HCl appears white in color, and that is why we can see the white fumes around the bottle of our anhydrous AlCl3. Now, my dear students, we want to study about the important trends in anomalous properties of boron. So we know that boron, being the first element, does not behave similar with the elements of the same group. And what are these anomalous behavior of boron? Certain important trends can be observed in the chemical behavior of group 13 elements. The first one, the trichlorides, bromides, and iodides of these elements, being covalent in nature, are hydrolyzed in water. So these halides are hydrolyzed in water, and they form the species like MOH4 minus, which is tetrahedral in shape, or they form MH2O6 minus 3, actually it should be plus 3, MH2O6 plus 3, which are octahedral in shape. We have seen the example of AlH2O6, my dear students, so I need not to explain it again. And they form the MOH4 minus, they are the tetrahedral. For example, if you look into the BOH4 minus, my dear students, BOH4 minus, this is how, and this is what it is, the tetrahedral shape. These species are formed in the aqueous medium. Boron does not form such species due to non-availability of vacant d orbitals. Thus, BOH minus 4 is possible, but BH2O6 plus 3 is not possible because the covalence of boron cannot be extended up to 6 because of the non-availability of the vacant d orbital in case of boron. The monomeric, this is M, the monomeric trihalides, being monomeric trihalide means AlCl3 but not Al2Cl6. Please remember. So this is monomer, this is dimer. So if we have monomeric trihalides like AlCl3 alone, being electron deficient, we are very well aware that they are electron deficient and are very strong Lewis acid. Boron trifluorides, that is your BF3, easily reacts with Lewis base such as ammonia to form the complex compound. We have already seen it. Let us revise it once again. BF3, which was having the bond angle 120 degree, the hybridization was sp2, it is planar. This boron present here is electron deficient, and as it is being electron deficient, my dear students, it accepts the 2 electron or lone pair from the nitrogen and make the tetrahedral sp3 hybridized complex NH3 BF3, and thus the octet of boron is achieved. So this is how the complex formation for BF3 is possible. It is due to the absence of d orbital that maximum covalence of boron is up to 4. Since d orbitals are available with aluminum and other elements, the maximum covalence can be expected beyond 4 for the elements other than the boron. Most of the other metal halides like AlCl3 are dimerized through the halogen bridge. Like Al2Cl6, we have even studied about the bridge dimer of Al2Cl6, my dear students. So I think you will be able to understand. But still, if you cannot understand, you can ask me. बच्चों समझ में आ रहा है?
Yes, sir.
Thank you. The metal species complete their octet by accepting the electrons from the halogen in this halogen bridged molecule. So aluminum or the other halides, they complete or achieve their octet by making the dimers. Now we have a question, my dear students. Boron is unable to form BF6-3 ion. Give reason. So due to the non-availability of d orbitals or vacant d orbitals, boron is unable to expand its octet. Therefore, maximum covalence of boron cannot be exceed 4, and thus boron can form BF4 minus, but boron cannot form BF6 minus 3. So here we complete the study of group 13 elements, and my dear students, now we are going to start our study of group 14 elements. Group 14 elements are collectively known as the carbon family. Dear students, can you see the screen clearly?
Yes, sir.
Do you
Yes,
have
sir.
any doubt?
No,
सर
sir.
मोनोमर मतलब
No,
क्या
sir.
होता है?
Monomer matlab single unit. See, if we write AlCl3, this is one molecule. This is one molecule. So it is what it is known as monomer. But if we write Al2Cl6, which has two molecules combine to make one molecule. Such one molecule in which two molecules are combined, this molecule is known as dimer. Please understand well, my dear students, here we have taken two molecules. But if the number of molecules is very high, we will call it polymer. You might have studied about polymers into your standards like 6, 7, 8. Have you?
Yes, sir.
Okay. So this is how, mer means the repeating units, mono means single. So when we have single unit, it is monomer. When we have 2 units, it's dimer. When we have 3 units, it's trimer. When we have 4 units, it's tetramer. So same way as we go, like as the number of units increases, lastly we call it polymer. So I hope now it is clear to you. Who asked this question? May I know the name?
Sir Anurag.
Anurag, समझ में आ गया बेटा?
Yes, sir.
Okay, can we move forward?
Yes, sir.
What you can see on the screen?
Carbon family.
Okay, so let's move forward and understand the carbon family. Carbon C, silicon Si, germanium Ge, tin Sn, and lead Pb are the members of the group 14 elements which are known as the carbon family. So these are the elements which are present into group 14 and they are the carbon family. Carbon is the 7th most abundant element by mass in the Earth's crust. Please remember that carbon is available in a huge amount into the mass in the Earth's crust, or carbon is widely distributed in the Earth. Carbon is widely distributed in nature in free as well as in the combined state. In elemental state, carbon is available as a coal. You might have studied about coal into your previous standards. So this coal is completely a carbon. It is also available in the pure form of carbon or elemental form in graphite. It is also available as a diamond. In combined state, even in 10th standard, my dear students, we have studied about the allotropes of carbon and the various like graphite, diamond, and fullerene also. In combined state, carbon is present as a metal carbonates, hydrogen carbonate, metal hydrogen carbonate, and it is also present as a carbon dioxide or carbon monoxide. Yeah, thus this carbon dioxide gas is available in the air 0.03%. One can emphatically say that carbon is the most versatile element in the world. Even in 10th standard, we have studied the versatility of carbon uh, or versatile nature of carbon. Combination of carbon with other elements such as dihydrogen, dioxygen, chlorine, and sulfur provides an astonishing array of the materials. So we can see lots of materials produced by the carbon, ranging from living tissue to the drugs and plastics and organic chemistry. So my dear students, carbon is found here and there all around the environment and everywhere, even inside our body as well as the outside our body. Organic chemistry is devoted to the carbon containing compounds. So there is a special branch of chemistry, my dear students, where we study only the compounds of carbon, and that branch of chemistry is known as the organic chemistry. This P block element chapter falls into the inorganic chemistry, but the next chapter, whatever we are going to study, they falls into the organic chemistry, where we will study about the carbon compounds. Carbon is an essential constituent of all living organisms. So all living organisms are essentially formed by carbon. Naturally occurring carbon contains two stable isotopes. One is 12C14 and another is 13C. So the atomic mass varies, my dear students. We should write them in this way: 12C14 and 12C13. Uh, this carbon is available into these isotopes also. In addition to this, my dear students, we have 14C isotope is available, which is a radioactive isotope, and it is used for the carbon dating. Carbon dating. Let me explain you what is carbon dating. Now see, but first let me read. It is radioactive isotope with half-life of 5770 years and used for the radiocarbon dating. Now what is this radiocarbon dating? So my dear students, suppose you have a tree, or you have a wood, or you have a rock which is having rock that has carbon available. Now, some or the other way, with huge amount of carbon atoms, some of the carbon atom present, them they are 14C, which are radioactive. Every 5770 years, their amount has been decreased to half. So initially, if they are 1 kg, after 5770 years, they will become 0.5 kg. That is 500 gram. Now, after 770 years, they will become 250 gram. After 770 years, they will become 125 gram. So, if we find out at present, my dear students, suppose we get one rock or we get one wood, and we find out what is the amount of carbon, C14 present into the wood or into the rock, we can easily estimate. See, we cannot say it surely, but we can easily estimate the age of that rock. We can easily estimate the age of that wood, and thus by estimating the age, or for estimation of the age uh, of the ancient rock or ancient wood, we can use this carbon, that is 14C, which is radioactive carbon, with the half-life of 5770 years, and this process is known as the radiocarbon dating. So this is how, my dear students, using the 14C carbon, we can have the radiocarbon dating, by which we can estimate the age of the old rock or old wood. I hope it is understood, my dear students. If you have any doubt, you can stop me and ask me. Hello?
No, sir, no doubt.
Thank
No,
you.
sir.
That's great. Silicon is the second, that is 27.7% by mass, most abundant element in the Earth's crust, and silicon is present in the nature in the form of silica. Your silica is SiO2, my dear students. If you look under your feet, you will find very small particles of sand. These all particles of sand, they are nothing but your silica, and you will find silica present all around you in the nature. So this silica, which is SiO2, is easily found in nature, and it is very abundant into the nature. So majorly our silicon is found as a silica, or it is found as a silicates. Silicon is very important component of ceramics. Ceramics is something that you used to use as a chinai mati. That is what we call it, chinai mati. Or we can have our cups, tea cups.
Chini mitti.
Yeah, chini mitti, tea cups and saucers. So we have these tea cups and saucers, my dear students. These tea cups and saucers are made from these ceramics. So now you understand the meaning of ceramics, my dear students. Someone has helped me. So silicon is very important component of that ceramics. It is very important component of glass. It is very important component of even cement. Germanium exists only in traces. So germanium is available in the earth, my dear students, in a very small amount. That is what we can understand. Traces means in a very small amount. Tin, that is your SN. Tin occurs mainly as a cassiterite or SnO2, and lead as a galena, that is PbS. So these are the various ores and how these elements occurs in the nature. That is what we can easily understand. Ultra pure form of germanium and silicon are used to make transistors and semiconductors devices, my dear students. So we have radios, which are Akashvani radios. These are all made up of these transistors and semiconductor devices. You might have heard about triodes and diodes. If so, they are made up of these semiconductors, germanium or silicon. Now, my dear students, we have the electronic configuration of our this group 14 elements. Valence shell electronic configuration of group 14 element, we can write it as NS2, NP2, but again, the inner core electronic configuration, of these elements differ from each other. You can see on the screen, I have written the electronic configuration for all these elements present in group 14, carbon, helium 2s2, 2p2, silicon, neon 3s2, 3p2, germanium, argon 4s2, 3d10, 4p2, tin, krypton 5s2, 4d10, 5p2, lead, xenon 6s2, 4f14, 5d10 and 6p2. So my dear students, this electronic configuration is very similar in this case of group 13 and group 14. You can see that the last element has got these 24 extra electrons filled after 6s2, and that is why these two electrons present in 6s, they are highly attracted by the core, and they behaves as an inert pair. So we will study about the inert pair. Same way, my dear students, here also these d electrons are added, and thus we can understand the various physical and chemical property change if they are observed in these elements too. That is what we have studied into the group 13 elements. Now, my dear students, let us start studying about the covalent radius of group number 14 elements. So these are the periodic properties that we start studying. There is a considerable increase in the covalent radius from carbon to silicon. See, carbon has got 77 picometer, but silicon has got 118 picometer. After from germanium to lead, small increase is observed. You can see that germanium has got 122 picometer, tin has got 140 picometer, and lead has got 146 picometer. So this increase is even not so big, but you can say that still there is an increase into the radius. This is due to the completely filled d and f orbitals in the heavier members. Now we want to study about the ionization enthalpy. The first ionization enthalpy, that is delta I Hi, is higher for group 14 elements as compared to the group 13 elements. So as compared to the group 13 elements, the first ionization enthalpy of group 14 element is higher. The influence of inner core element, inner core electron is visible in group 14 too. So you will see some of the properties which are disturbed by this inner core. But in general, we can say that the value of ionization enthalpy decreases down the group, and big decrease from carbon to silicon. But from silicon to germanium to tin, there is a small decrease that is observed into the values of ionization enthalpy in group 14 elements. From tin to lead, my dear students, a small increase is observed. This is a very important point. If you can recall or if you remember, when we go down the group, the value generally decreases, but from tin to lead, my dear students, a small increase into the ionization enthalpy is observed, and that is what, because of the 24 electrons filled into the inner shell, 14 in 4f and 10 electron into the 5d. Why delta IH for Sn or tin is lower than the first ionization enthalpy of lead? So let us understand this concept, my dear students. Uh, Generally, what happens going down the group, my dear students, the ionization enthalpy decreases. So if we go down the group, generally what happens? This ionization enthalpy decreases. But going from tin to lead, the first ionization enthalpy value increases. This could be explained using the inner core electronic configuration. You can see the electronic configuration for tin is krypton, 5s2, 4d10, 5p2, but for lead it is xenon, 6s2, 4f14, 5d10, 6p2. In case of the lead, if we look at, we find that after 6s, 14 electron goes to the n-2f orbital, which is near to the nucleus. Thus, atomic number is increased and the nuclear charge is even increased. But the 14 electron goes to the n-2f orbitals. Apart from that, my dear students, what happens where the 10 electron goes? That is also important. So after this, after this filling of the 6s orbital, 4f orbital filled, and then 10 electron, my dear students, 10 electron goes into the n-1d orbital, that is 5d orbital, which is even near to the nucleus. Thus total 24, 14 plus 10 electron goes into the inner shell. The effective nuclear charge is increased, but due to the poor screening of f and d orbital, the effective nuclear charge attracts the 6p electrons well, and thus the electrons are difficult to remove from the 6p orbital. Thus more energy is needed to remove 6p electron as compared to the 5p electrons in tin, and thus the first ionization enthalpy of tin is lower than the first ionization enthalpy of Pb, same as that as we have studied about the indium and thallium. So the same way, my dear students, the same is the case here, and that is why the first ionization enthalpy uh, of our tin is less than the first ionization enthalpy of lead. Now let us study about the electronegativity. Due to the small size, the element of this group are slightly more electronegative than group 13 elements. So if you compare the electronegativity, group 14 elements are more electronegative than